Hey there, y'all. Today we're going to look at 1.6. We're going to separate this into two sections. So today we're just going to look at the first half on graphing systems of equations. And so the two objectives we got, the first one will be to solve systems of linear equations graphically, and the second will be to solve systems of linear equations algebraically. Again, we'll look at the algebraic part in part B of this section. And so our standard, like from section 1.5, ACE.3, using systems of equations and inequalities to represent constraints arising in real-world situations. Remember, we want to solve such systems using graphical and analytical methods, including linear programming, and interpret the solutions within the context of the situation. And so let's talk about the methods to solve a system. So the 6 methods of solving a system include these: a table, solving by graphing, solving by substitution, solving by elimination, and then we have 2 methods you'll see here highlighted in yellow. Those are methods that we'll talk about either later or in a later course. And so matrices is a method that we may look at if we get time, and Cramer's rule is a method that if you continue on to calculus, you'll see there. And so let's look at how to solve a system by a table first. So in this first example, we're going to look at how to solve the system of equations by completing a table. And so we're given x plus y is equal to 3 and negative 2x plus y is equal to negative 6. And so you'll see we've set up a table here, and we're going to plug in x values for us to then find the y values of these 2 different equations. And so I'm first going to start with x being 0. And we plug in 0 for x to this. And so 0 plus y is equal to 3. And so y would be equal to 3, of course. Now, one way that we could look at this and make it a little bit easier on us, and we'll do that after this step, is we can solve these both for y first. But let's finish this step here. So if I plug in 0 for this equation, negative 2x times 0 is 0, plus y is negative 6, so y is equal to negative 6. Okay, so we can reorganize these so they're both set equal to y. And so subtracting the x here, we're going to get y equals 3 minus x. And in the second one, y is equal to positive 2x minus 6 after adding the 2x to both sides. And so when we look at this, we want to see, is it going to get closer or further away? And so I'm going to plug in 1 for both. If the 2 y values begin to trend closer to each other, we're headed in the right direction. If they're headed away from each other, we need to change and go towards the negatives and get this going the right way. And so when I plug in 1 here, 3 minus 1 is 2. And I plug in 1 here, I get 2 times 1 is 2, minus 6 is negative 4. Well, I first went from 3 to negative 6, that's a span of 9. And then from 2 to negative 4, the span there is only 6. So I'm headed in the right direction. So I'm going to go to 2. And so we're going to do the same thing. We plug in the 2 for both x's. 3 minus 2 is 1. And then 2 times 2 is 4, minus 6 is negative 2. And if I go to 3, watch what happens. 3 minus 3 is 0. 2 times 3 is 6. And 6 minus 6 is 0. These 2 values have come out the same. And so if I'm looking at a table to know where this system is going to be solved, I'm looking for where the y values are going to be the same for the same x value. And so where do these 2 lines intersect? They will intersect at the point 3, 0. Now, is it always going to be at something with a 0 in it? No. That's coincidence in this problem that it happened to be the x-intercept of both of these lines. We could end up with an intercept at 5, negative 3. But that's if both lines have that point, 5, negative 3. Because remember, when we're talking about solving a system, we're talking about where do these 2 lines intersect. Okay? So that's what we're looking at in example A. As we look at example 2 on solving by graphing, and so we're going to graph these 2 equations on the coordinate plane and find where they intersect. Now remember, if they're really simple equations, we're going to just graph them on the coordinate plane, find where they intersect, and be done. If they're really complicated cases, we could use a graphing calculator or a program like Desmos to graph those 2 lines and take care of business. Now in this one, they're both given in standard form. Your option, if you want to keep it in standard form, find the 2 intercepts, or solve these both into slope-intercept form and get the y-intercept and the slope and graph that way, or a mixture of the two. Just depends on how you want to do it. So for this first line, I'm going to leave it in standard form and find the two intercepts. And so plugging in 0 for y, I get that x is equal to 0, and y would be equal to 0, because if I plug in 0 for x, I still get 0 for y. So this one actually doesn't help me draw this line, because the problem is I've got 1 point. It crosses at the origin. And so we actually have to solve this one out, unfortunately. So negative 2y is equal to negative x, and we divide by the negative 2, meaning that y is equal to positive 1/2 x, meaning that my slope from the origin is going to go up 1 and right 2. Now, when you're dealing with systems, you need to make sure that you draw these lines as long and straight as you can. Because if you don't draw them long and straight, you're going to have an issue with finding the intersection. So make sure you pay attention to those points. And we want to keep them going up and right all the way to the edge, and then down and left all the way down the other way. And when we draw this line, we want to make sure it's nice and straight, hitting all of those points. And now we'll do the same for the second line. And again, we could determine this by doing it in standard form, or we could do it in slope-intercept form. And so plugging in the 0 here for x, I get that the y is equal to 6, and plugging in 0 for y, I get that the x is equal to 6, so I get a line that looks like this. And we can see that our slope is down 6, right 6, and if I have enough space, I can go up and I can go left. But we're going to see what happens here is that these two lines are going to come down like this and come through and through and through to there. And so we're going to see that we have a nice intersection here. Where do these two lines meet? They meet at the order pair 4, 2. Now, how do we verify solutions of a system? We need to plug the order pair that we find back into both equations. And so we're going to do the first one, x minus 2y equals 0. Well, 4 minus 2 times 2, is that equal to 0? And so 4 minus 4 is equal to 0, so 0 is equal to 0, that checks out. We do it for the second one as well, so x plus y is equal to 6, so 4 plus 2, is that equal to 6? Well, obviously 6 is equal to 6, so it checks out for both, which means that we have the right point, and this is the solution of this system. So now we're going to look at example B. I want you to take a second and pause the video now and look at example B. Try this one out, graph it out. Again, pay attention to the information you're given and what forms would be best to solve it from, if it's slope-intercept or from standard form. So pause the video here and then let's look at this example together. Alright, I hope you paused the video. So we're going to look at x plus 3y is equal to 7 and y is equal to 2x plus 3. So this first line, we could find the intercepts if we wanted to. The x-intercept is going to be really easy. It's 7. The y-intercept is the one that's a little bit more difficult. It is going to be 7/3 when we find it. Or remember that we could solve this for the y and get that information as well. And again, we're going to get that fraction in that problem as well. So we're going to subtract the x and get 3y is equal to negative x plus 7, and dividing everything by 3, we get y is equal to negative 1/3 x plus 7/3. And I know some of you are like, oh my god, where is 7/3? 7/3 is 2 1/3, and so that is here. But like I said, the x-intercept of this problem is 7, because when we put 0 here for y. And so I could plot those 2 points, and we can go with our slope, right? So from this point, we can go up 1, left 3, up 1, left 3, up 1, left 3. So we're here, and we're here, and we're here, and we can keep going. We can go down and right as well, and then up and left, and so we get this line to start for our first line. So now we look at the second line, y is equal to 2x plus 3. That's already in slope-intercept form, and so just graph it like you're used to, right? So the m is equal to 2, the b is equal to 3, and so we're going to start at a b of 3 and come down 2 and right 1, down 2, right 1, sorry, not down 2, this is a positive slope. So let's back that train right up. We're going to go up 2 and right 1, up 2, right 1, up 2, right 1. Sorry about that. So down and left, down and left. And so we end up with this line here. Now, is that a really nice thing to see? Well, the intersection's somewhere in that little gap, right? It's to the left of the y-axis, and it's above 2 for its y value. So it's going to be like negative 0 point something, comma, 2 point something. The question is, what are those decimal values? And we can estimate, we can kind of guess where it is, because we know it crosses the y-axis at 2 1/3. So the likelihood is this is probably somewhere near 2 1/2. And that being the case, this one would be probably negative 0.25. And that's based on knowing how far it's moving down and left as we're going that direction from the blue y-intercept. So again, pay attention to your points. But we could graph this on a system like Desmos or on a graphing calculator and find these values precisely to get the values in the end, especially when we need it exact. And that's why graphing is not the best method to solve most times. Like if we're looking for a quick answer or we're looking for an approximation, it's great for those things. But if we want a precise answer, we're going to want to do it by substitution. We're going to want to do it by elimination. We're going to want to do it by matrices or Cramer's rule. Again, Cramer's rule is for a lot higher cases. But we're going to want to use a method that gives us a precise answer and not an approximation. So again, we'll talk more about that in the second half of this lesson. All right, so let's continue on and look at one more thing. So there's a couple of terminology you need to know about systems. The first is that a system can be defined based on the number of solutions it has. And so when we think about a system, right, we could take two lines like these two pins here, and most systems are going to cross, and we get how many solutions? One, right? Because where they cross is the solution. And so that's our general case 95% of the time. But what else could these two lines do? Well, think about it. Like if I took these two lines and I put them like this, they're now what? They're parallel, right? And so solutions happen when the two lines touch. Where do these two lines touch? They don't. That's the point. So how many solutions would this have? None, right? And so that's case 2. Case 3 is this, that these two lines aren't parallel, they're not intersecting, but the two lines are the same line. And so remember that solutions are where the two lines touch, right? Where do the two lines touch now? Well, they touch along every single point across this graph. And so that's the way we'll classify systems, based on the number of solutions. And so the first terminology here is that a system is consistent if it has at least one solution. So again, a system is consistent if it has at least one solution. And so if it's consistent with at least one solution, that means it is inconsistent if it has no solutions. If a system has exactly one solution, so again, it's still going to be called consistent, but now we're going to use a second term here for those that have solutions. This term is that if a system has exactly one solution, it is called independent. So it would be a consistent and independent system. And if it has an infinite number of solutions, it is still consistent because it has at least one solution. But the second term we're going to use is dependent. And it's dependent because the two lines have to move in unison, right? Because if I start moving this line, I now end up with no solutions. Or if I move the line from like this to like this, I end up with now just one solution. So these two lines depend on each other. When my two lines are like this, they're considered independent because this line can move independently. It changes the solution, right? But it doesn't matter about this line. This line's still going to be in its place, but if I change this line. So let's say we're talking about like a taxi cab that raises its fares, and we're talking about Uber that has a different price point, right? And so we could be talking about, okay, if I go so many miles with Uber or so many miles in a traditional taxi, what's going to happen, right? Well, if I change the price of the Uber, if I change the price of the taxi, it only affects that one line, but it does change the solution of where it will be. So as we look at this last example, we've got a pair of graphs that we're going to look at. We want to graph the system and describe if it's consistent and independent, consistent and dependent, or an inconsistent system based on the terminology we just talked about a second ago. And so when we look at this first equation, we got 15x minus 6y is equal to 0 and 5x minus 2y is equal to 10. We want to graph those two lines on the coordinate plane and see what we get. So I'm going to draw these two lines and then they'll pop up on screen for you, and if you need help graphing them, come back and look at the first couple examples on how that was done. Alright, so I've graphed these up here. The blue line is the first one, the 15x minus 6y equals 0, and the second is the red line is the 5x minus 2y is equal to 10. And so you'll see the work here off to the side of what I did there. But when we look at these two lines, what happens? These two lines end up being what? Parallel. And so what type of system is that? Remember, to be consistent, it has to have at least one solution. If it's inconsistent, it has no solution. So which one is this? It is inconsistent, because these two lines are parallel, they're never going to touch. And how do we know they're parallel? Remember, we talked about in the previous section, in section 1.4, that parallel lines have what? The same what? The same slope. And so these are parallel lines because they do have different y-intercepts. Remember, if these two lines were to have the same y-intercept and the same slope, they would be the same line. And so one last example we're going to look at, and I'll ask you to do that one on your own first. And so here is B. X plus y is equal to 3, and 2x is equal to 2y plus 6. So I want you to pause the video, graph this up. I'm going to graph it while it's paused as well, and then you can see how this works out. So you'll see I have these two graphed. The x plus y equals 3 is graphed in blue, and the 2x equals negative 2y plus 6 is graphed in red. And so what do we see with these two lines? They end up as the same line, right? And so because they will have at least one solution, they are consistent. So it's not C and it's not D, because none of the above is just a throwaway answer here. But which type of system is this? Are these two lines independent or dependent on one another? And that's the best way to think about this. If I move one of these lines, does it change how many solutions I have? It does, right? So this would be a dependent system because the two lines depend on each other being in the same spot to get those lines. And so what that means when we talk about solutions here, right, and this is the last thing I'm going to cover in this video today, is every single point along this conjoined line is a solution. So the order pair 0, 3 is a solution. The order pair 3, 0. The order pair 6, negative 3 is a solution. All those are solutions to this system because they are all points on the same line. And if you keep that in mind, that points, the solutions of this happen when the two lines touch, you'll remember that every point it touches is a solution. Okay, and so that's it for this first half of the lesson. We'll look at substitution and elimination in the next video for 1.6b. So again, make sure you check out that Google form, submit your questions, answer the questions in there, and I will catch y'all next time.